but I don't see the record icon. Okay, it's recording now. I see it. Okay. All right, this is Durward King with Samson Community College. This class is ELC 215, Electrical Maintenance for Automation Systems. And this is February the 16th. And we're going to be starting out on station 5 that puts the covers on. And we're going to be focusing on the encoder. We have a cylinder that measures the height of the caps, and it has an encoder built into the cylinder. It's a stroke reading cylinder made by SMC. And let's get our information up here. This Zoom ain't acting right. I don't think I'm going to be able to use it tonight. If it slows me down like this, I'm not going to be able to keep using it. Okay, it went to there. And let me go to cover. Okay, if you look on the screen, this is the schematic for station 5. And there was only 2 things different about 5 than the rest of the system. There's 2 things that are here that ain't nowhere else. And that is, one of them would be a photoelectric sensor. It's a photo eye. It's right here on the 1, 2 is the first sensor as it goes around. And it has an electric eye that reflects it. It puts a beam down on the part and it bounces back up. And it recognizes if it's a dark color or a light color cap. For those of you that won't hear, and where that sensor is, again, all the rest of them are. This is a repeat of what you're seeing. As a matter of fact, there's 4 types of sensors that it goes to around that turntable, and the first station is an inductive proximity sensor that's here. If we go up with it and go over, you have an inductive proximity sensor that picks up metals. That says here, metallic cover detection. So this is one you can identify on your symbol guide. Let me resync the screen share. Every time I change the screen, I have to resync it, or else whoever's out there is not going to see it. So it has the inductive proximity sensor and then the capacitive type. That picks up metals, that picks up plastics and metals. And so those were also on station 4. But a couple of y'all have been out for some nights, and I don't know if you have identified those on your symbol guide. Your symbol guide is this thing here. So if you scroll down in there, you'll find that you have you got a study guide there. Yeah. So look, right over here on this side, you've got that's the inductive proximity sensor right there. Inductive proximity sensor, and then with a normally open contact, and then the capacitive type is right here, which is like 2 down. You got the inductive type, and then you've got the capacitive type right here on your study guide. Have you got a study guide for symbols, Victor? We give it out like a few weeks ago. We gave it out. You got one. You want another one there to write on? Or? Yeah. All right, now let's go back to the schematic. So flip on. This is something that's new on station 5. That's not on anything previous. It's a photoelectric sensor, and the other night we did talk about it. But for those of you that have missed the other night, here it is. Right there. And so when you go to the input on the PLC, it says clear color detection. So it can detect if it's a light color, the reflection bounces off of it. If it's a dark color, it doesn't get that reflection back as well. It's a photoelectric sensor or detector. If you look here, the way the sensor is just a normally open sensor. It has a contact in it. But here's the way it works. The contact closes when the light that shines out of here bounces off of some object out here, like a cover. It comes out, bounces off of something, and then it comes right back and reflects back in. So it's a one-piece send and receive. It's got a for this one. It's not inductive, no. Photoelectric. If you go to Word Bank, yeah, because a photoelectric sensor or detector, because it works on image. It works on seeing. It shoots a beam out, and then if it reflects back into the other part of the sensor and it sees it come back, it closes the contact. Some photoelectrics are 2-piece. You got like on a garage door. For a garage door, you got a transmit and a receive, two separate pieces at the bottom of the door. That if you step in the door like that and it breaks the beam, that the door won't come down. This is the same thing, but it's a one piece. It's all built into the one round 18mm barrel rod. You take the sensor and look at it, it looks like two eyeballs. It's like a split. And one of them is a transmit, the other one is a pickup eye. And so that's what you're seeing in the now. So in the symbol guide, it's toward the end. You know, it's above that linear potentiometer on station 2. So photoelectric sensor normally open. And again, that's a close-up of it right there. So it has to have the 24-volt plus, the common coming in, and then it has a signal leaving it that's the 24 that comes in. The 24 goes here, and then it leaves right out of here, goes to the PLC. And it tells it when it has a clear cover or a light cover. Now, this particular input is in slot number 2 in the PLC. So it's, you know, you have the slot 1, slot 2. There's also, you know, there's a couple of slots on this one, extra modules. So it's slot 2, it's an input, and it's input 0 in slot 2. Okay. So this is one that you can test it with a meter to know and see is a signal is it getting there. Okay, now we move on to the encoder, which is we did start talking about this the other night. This box called a linear encoder. They've misspelled it. They got lineal, but it's linear. But that box right there, let's go look at the actual cylinder. Let me pull that document up. Now, everybody got one of these that shows a picture of the cylinder itself. So it's a regular pneumatic cylinder, but it's got a integrated encoder that generates pulses that leave it. It generates these square wave pulses that sends pulses out of that cable to a special high-speed count card module on the PLC. And the PLC counts those pulses, and it knows how far it travels, so it can actually measure something that the cylinder extends against on the end. It's got a little end screwed on it, and it goes against the part that we're measuring. It extends and it measures, and then this gives the information to the PLC so it can measure the piece that it's actually coming in contact with. It's a stroke reading cylinder, so it's like a smart cylinder. There's a couple of fine points about it. You know, it shows it plugged into a counter, but we're going into a PLC module. So there's different ways things it can go into, different applications of how they can, where it can be applied in the industry. Now, so here, let's take a look. Now, we talked about this the other night, how it works. Okay, all right. All right. How you doing now? Hanging in there. Okay, so there goes the cylinder right there. It has a magnetic scale rod. If you look closer at it, the rod itself has magnetic sections and non-magnetic sections on the piston rod. You got a sensor, and as the shaft moves, the sensor is stationary. As the shaft moves, it sends information out through the encoder, which it processes it. And there's two signals coming out of it. You got an A phase and a B phase. And the reason why they got two signals coming off of it is they use, it looks like a sine wave on the signals until it gets processed through this circuit. Then it looks nice and square. And then it's easy for the PLC to count because it has a definite leading edge and trailing edge on there. And the PLC can count the edges of the pulses whenever they turn it into a square wave versus a sine wave like that. But the reason for having two pulses is this. And whether you have a linear encoder that's a straight line encoder or a rotary encoder, most encoders are on the back of a motor on servos. So picture if you have a rotary motor, it's got a box mounted on the back of it with a cable. And wherever that motor turns at, it's sending all these pulses back to a controller, just telling the controller exactly where it's at in fine resolution, super fine. And so that the controller can know right when to stop it and then index it and step it to do specific, real precise moves on equipment. You know, any of you ever seen like a CNC mill or a lathe, an automated lathe move and do milling and stuff? They got servos, they got encoders. Every motor has an encoder on. So like in a machine shop, that's an easy thing for you to relate to. If you ever see like a lathe or a mill running by itself, every motor on there's got an encoder. It's sending pulses back to the control, and it's matching up with the dimensions of whatever that thing's being told to make and cut. Well, see here, the encoder is used for a different reason. It's used for positional, but for measuring something. But where in a machine shop, it's actually used to know where to cut so something is measured properly, so it's cut properly. You know, if you're cutting a shaft or whatever you're doing, so it's still for measuring purposes. It's still for measuring position, very precise position. Now, the reason for the two signals. So why does it need two signals? It says that right here. This is the root reason why they have two signals. When the movement is expressed by a single line of pulses, it is impossible to accurately identify the current position because the pulse waves appear both upward and downward directions. A and B phase difference output, two lines of pulses are provided that where one line detects the movement and the other distinguishes the direction that you're moving in. So they've got an A phase coming out of the encoder going to the PLC to one particular input. The B phase goes to a separate input on the PLC. There's two inputs. And the second signal coming out of the encoder, look at here. When the signal goes up and it gets about halfway, that's a 90-degree point right there. If it was a sine wave, if you go over, let me draw this. Do it like this. In its natural form, if you have a sine wave, this is what comes in from the power button in the bar. And this here is 60 degrees. This here is 90 degrees. And the continuous cycle will be 360 degrees. That will be 180. And you can consider that to be one side. Okay? If you've got 360 degrees in that blade there, when you look at square blade, it's got square edges to it. The halfway, once it goes high, the halfway point between here and here will be the 90 degree point. And that's the point where if the 90 degree point halfway is where the next one starts. So if anything is 90 degrees behind, 90 degrees behind. But it's hard to say, well, how long is the 90 degrees there? Because when you originally form the signal, you put the sound plate, that's how you determine where it is if it swings as far as degrees. This would be a complete cycle, 360, this is 90 degrees, so the complete is backward. But they convert it from the sound plate over to the square plate, a halfway point here is 90 degrees. So that point, that's where the second start. They use this signal here to determine if it's still is actually extending or contracting. That's the purpose of it. That's, they watch it to see. That's how they know if it's extending or contracting. So that just a rotary that goes on the motor, they look at the feedback, and they know if the motor is clockwise or counterclockwise based on that feedback and motor to that. That's what they do. The only thing for me and you, the only thing for me and you to be concerned about is this. Is it seeing two signals out of all? And can you see it on scope? And that's it. It either is or not. You know what I mean? We got a device that you can see on the screen, and all we need to do is make sure you come over and prove it. Outside the cell up and down, I want you to see the two sets of signals at the same time on the screen, and if you see that, then you know it's fine. And that's how you can do it if you come down. You have to have that scope, that scope meter that draws the picture for you. What a regular meter wants. Regular meter can't really do something like that. That's so bad. And you can't see a picture of it. Now there's a caution about that cylinder. They tell you don't turn the shaft on that cylinder because it'll damage it. So if you, and I'll show you where it says that at. And it's all about the way it's designed in there. If you rotate that shaft, if you take a wrench and try to rotate it, it's not going to rotate easily because of the way it's made, the way it's actually connected inside with the encoder. But if you try to rotate it, you'll ruin the encoder because it's not made, the cylinder's not made to rotate. It's made to just go in and out. Okay. So there's a place in here to where it tells you not to put a wrench on, not to rotate it mechanically. Go to page 10-12-6. Now right here, it tells you right here. They don't want you turning that. Now, whatever you screw onto the end of it, the attachment that screws onto it, you would want to keep the shaft stationary while you thread that attachment onto it. You know what I mean? And keep the shaft stationary while you screw that little wedge lock onto it. And do the lock nut. So you would want to keep the shaft still whenever you attach that stuff and lock it in. So that's the caution right there that it would ruin it. Okay, so now we'll just move right along to using the oscilloscope to do a quick measurement, and then we'll move on to station 6. That's all we want to do. You're just going to see what's different and how would you use it. Because when I bug them, you might want to say, hey, can I get the scope out and let me check that encoder? That might be something that you want to check. Let's go back to the schematic. This stuff, where is that? Excuse me. Okay, we're back to the schematic now. I'm going to zoom in, and we'll talk about how do you those of you that missed the other night in the electrical lab, it wants you to explain how that encoder is actually wired. So let me flip real quick to the lab sheet and show you where that is, and then we'll proceed with our readings here. So if I go, let's go back. It is. Oh yeah, 5. Mm-hmm. Yep, 5. Yep, it is. Okay. So you need this right up here. You need the electric lab, right? 5. Okay, let's do that. Does everybody have the station 5 electric lab? I don't have it. It's passed it out. Yeah, I mean, I'm passing it out. Okay. Yes, sir. This might be about the point that where you had to drop that last time. You did. You did. So, had you started troubleshooting it? Okay. Right. But you just had to. You probably about the time we started doing the actual troubleshooting when you had to get out. Okay. Yeah, you missed the best part. Yeah. Yeah. So you get it this time. Okay. So when you look through this section here, the part that it wants you to describe how the encoder's hooked up is right in here. Well, for one thing, it wanted you to measure on the encoder. It was asking you to check voltage without a cap, with a low cap and a high cap. Now this is like a trick setup here, because you can't measure the voltage with a meter. You got to have a scope to do it. Okay. So this section here, when you use the oscilloscope, I'm going to let you draw those square wave pulses in here and explain, and let that be your reading. I'll let you draw, the pulses that you see, because you're not going to measure voltage with a meter. It'll never read it. It's going to be garbled. It's going to be all garbled up. The display will constantly be flickering around, changing, but you can draw the square wave pulses whenever you see it right in there. For 5, you don't have it. Okay. Didn't I leave you one out there? I didn't leave you one out there. The 5, I didn't. Okay. Right in here, it wants you to explain how the connection is done of the linear encoder. So sort of in a nutshell, what you want to be able to say as far as how it's wired. We go back to the schematic. Now, this is the encoder that's mounted to the side of that cylinder. It has to have the 24 volts. That's 24 volt neutral. just say that the encoder requires 24 volts DC for a power supply. It requires that. There's a couple of jumpers in there that are required. You can say it also requires a couple of jumpers. You don't have to be specific. And then you can say that the encoder has two outputs. It has an A and a B output that go to two different inputs on the PLC. And then you can say that both of those outputs, they require a special resistor. Each output requires a special resistor to be connected between the 24 volt line and each of the outputs. This is called a pull-up resistor. There's not enough time to get into the reason behind the name of that, why that is, but it's called a pull-up resistor. The type of output, the type of transistor outputs that this have is it has to have a resistor, a 470 ohm resistor between the 24 volt. That's a resistor right there. If I enlarge, that's a resistor. That's a 470 ohm right there, and it's between the 24 volt and each one of the outputs. It looks very unusual, but it's required to have an interface between the encoder and the PLC input. It's a requirement to go between that SMC encoder and an Allen Bradley PLC input module. You don't have to know anything beyond that. It's a special. Those resistors are there. They're special for the interface to let those things interface together and talk and agree and communicate. That's all you got to know. So those two resistors are actually on the terminal strip. They're small, and you can find them if you go if you hadn't need to go to where they were. If you wanted to look at them, you go to the last page in this schematic set, and you'll see them that are right down in there. If you go in, so on the X3 layout, X3 strip, you'll see two little resistors that are actually mounted, terminated there at the strip. And there they are right there. If you go in big, you'll see that what they are. They'll have color codes. There'll be stripes on them. I could get into it and teach you how to read the stripes if you wanted to. Right now we don't need to, just to know that they're connected between 24 and I-22, and also between 24 and I-23. And that's where they're landed at. That's how they connect between the encoder terminals and the PLC input. Okay, it's something special that has to be there for those. Sometimes when you have two different brands of things talking to each other, you got to have something in there to help with another component to make it work for interfacing reasons. And that's just what it has to have. We don't have to get into the house, to the whys. We just know it has to happen, you know. So all we want to do right now is here's what I want you to do. This device here is called a scope meter. It's got a screen on it. It's about $3,000, and it will read things that nothing else will read. About $3,000. Yeah, that's the cheap one. This is the cheapest one. That's the bottom end. That's the bottom end on a scope meter. Bottom end. They go up from there. I wish I had one, even a little faster than this one. I wish it did, but it's fine. Butterball bought this. A 123. It's a Fluke 123 scope meter. Yep. But it'll show you. It has on here. Look. It has two channels or two traces. It's a dual trace. It goes a dual trace. It'll give you a split screen, and you can read one signal here and another signal there. You can read both of the pulses with this on that screen by doing a split screen. And you can know that that encoder is good or bad with this thing. No doubt about it. You can tell them guys it's good or it's shot. Without check for sure. Okay. So that's, again, nothing else is going to read it to something like this. You may get one of them out once a year, maybe a little more than that. But if you know how to use it, then you can avoid. A guy yesterday with Butterball in here told me that they're not using that of it. I said, well, look, Butterball sent this thing. You need to find out whoever's got that thing over there. Somebody's got one. And you need to ask them who's got it, put it hid somewhere. They got one, or they would have sent me this one, to use to teach. He said they change encoders out from time to time, guessing because they don't know for sure if it's bad. They'll change it out. Now that ain't what's wrong. And they kill all that time and put a brand new encoder, as fragile as they are, on a machine, and it wasn't even bad. It might have been the input module or something, So that's kind of thing where it's a rare thing to use, but you need to know how to use it if you're going to be in a plant. So anyway, so here's how you'll hook it up. You're just going to go these probes here. You have a red channel and a gray channel, and you're going to go to those two signals, and then you have a common. Three probes here. You got two channels and a common, and so you got to get all those just right on the PLC module, and to be able to see both of those signals. And it's going to take us a minute to get everything tuned in with the screen to be able to see both of them. Once we do, then everybody can come by in pairs and do it and read it. And I'll jog the cylinder up and down real slow, and you can see the pulses. And what we're going to do would work whether it's a linear or whether it's a rotary, like on a motor. If it's a motorized, a round encoder that spins for a motor, you can read it the same way if you can get your terminals. And now, there's not many people around that can identify what we're saying here. A lot of folks don't know how to do this. And in Butterball, everybody doesn't even know that they got an encoder. They don't even know that they've got a scope meter, but I know that they do. Somebody's got it, it just hadn't been broadcasted. So you're going to measure. You go directly to this input on the PLC, directly to this one, and then the common. Wire 25 is common. So you'll put, say, the red probe on I-22, the gray probe on I-23, and then the black common probe will go on wire 25. But all of those will be easy to see on that module. Okay. And then I'll do a manual override on the valve and I'm going to slow it down so it goes nice and slow, up and down, and then we'll be able to read those pulses. I'm going to put the camera over here in front of the scope so that while we're doing this, it can be seen by whoever's sitting down or whoever might be watching. So let me get this here position. And y'all can come over in pairs, just two at a time. And you can watch the screen. It's going to take a minute or two to get the adjustments right here so it can be ready good. It's kind of thin to get those ready. We'll cut the screen share off. Now, so let's go. Let's get everybody some gloves on. Let's put on our gloves. We're putting these on because we're going to be dealing with hand tools that other people use, the computers, the laptops. They're being used by other folks. So
you ain't gonna get much.
We don't.
I might got an extra penny in my pocket. We might have a problem.
If you come around, we'll get your gloves there as you come around.
You might have better look with that.
If they stop construction over there, you're gonna laugh. They're gonna walk around and cover that.
We're not writing numbers, we're writing the post.
You're gonna draw, you're gonna draw, you're gonna draw, the folks, you're gonna draw.
When you're asleep. I'm gonna admit it. I didn't think about that.
Lastly, this is the model line. Got slot 1, 2, it's actually slot 3. Let's get now, let's get on. I'm gonna let you get in position out here with the pros. I'm gonna jog it up and down, and I'm probably gonna have to fiddle around with this display a little bit.
I know it was 25. What was the other two?
Let's get up from there.
Yeah, I can't remember
I think it might have been I-22, I-23.
I think you're right.
It was I-22, I-23, and then 25.
And 25 for 25. Yep. That's it.
Right?
That's right. And, you know, just keep the plugs, don't let the plugs touch each other, keep them separate. And, you go straight to the, go straight onto the mod. Yeah, straight into there. Yeah. Mm-hmm. Yeah. Yeah. And then I've got a job that let's make sure it's in manual. That's good. Yeah. What's the number of this cylinder right here as far as the web? L. So we're gonna go to L. Now we got to cut the air on because somebody pressed the start button on the first station.
Hey, this one's not turned on at all, there.
All right, you go ahead and cut it on. I thought I had these on here. Okay, yeah. Let's cut.
It helps.
Let's cut all of them on. Cut the power switch. We got to have all of them on.
That one else thing is on. I can't tell.
If the belts ain't on, then they ain't on.
Well, I can't tell from here. Yeah, it don't look like it's running.
You cut that's actually on there, but the e-stop here must not be released. You got to twist it. So now it come on. Somebody hit the e-stop. See, it's fine. It's fine. You see the lights on.
Right.
Now it's got to boot up. When after it boots up, then the belt starts running. Yeah. If you go up to one and hit the power switch and the lights don't come on immediately, you rotate the e-stop and it'll pop out. When you push it, it locks in, and you got the twist and let go of it, bam, and it comes right back at it. It gets a twist to release. I don't particularly like them. I like push pulls. That's the twist to release. Anyway. This table's too slick. Let's get something up there that ain't gonna move. Now, let me get some, so what's the letter here? L. L. Now, we're gonna slow it down even a little more than that. The bottom, go ahead with it a little bit. Go ahead just a little bit at the bottom. And also the top. We're going to get a little slower so you can see you can read the phone. That looks good. That's pretty good. It'll be easy to read the pulse once we start giving.
Well, you can see it. You can see it dancing around.
Right, you see the pulse is there? Now, so now we got to get it where you can see both. I got to enable the other channel. The other channel's not turned on right now, so let me get around here. Well, you're getting one. Look, it has to be moving to watch it. You see the pulses in there? You see the pulses that are there? Mm-hmm. Now, you're reading one channel. We got to get the other channel turned on. I don't have the other channel turned on yet. So the way you have to enable it, now I've got if y'all remind me, I've got a guide. I need to get copies in here, a guide about the scope, or you can download it online to your smartphone, a Fluke 123 scope, if you want to get the information. But you have to enable, let me get it flipped around, and I'll shoot the screen on it, you can see. How to get it set up where to now it has the two channels coming into it. And I've got to go in the menu and enable the other channel. So I got to go into, let's see. If you notice here, it says input B is off. You see that? Input B is turned off. I got to get it on. Everybody see that? I've got it so that it uses the entire screen for one signal. You get the bigger screen for one signal. So we got to come over to here. I moved it up and down like that, and now you get enter. Enter's over here, F4. And now it's going to give me two screens, okay? And then let's see, getting out of this thing. Now I have two signals. You notice the two lines that are there? Now I'm probably going to have to move that bottom one up. So let's jog it one time and see what we got. I'm going to let go of it. Now, I'm going to adjust the time on it, the resolution of it, so that it's easier to see. And the way you do the time adjustment is you go to where it says time in seconds or nanoseconds. And I can adjust the time of it here so that it'll be, well, right now it's 5 milliseconds per division on the block, those little blocks. If I adjust it, if I hit time on nanoseconds again, it's 2 milliseconds per division. So it lets me magnify and get in and see more magnified, okay? We're going to go to L again. Now, you see it's more defined because it's magnified, see? You see the pulse is there now? You see close? So So it's clearly defined there. And it slows way down. You see it? But all you've got to see is just for a split second that they're both there. They're not there for a long time because the stroke it doesn't take long. You know what I mean? Do it again. If we can even make the contrast be darker, let's see, the contrast is over here. I hit contrast and go. That's lighter, and I hold that in, it's going to go darker. It'll be darker, sharper looking. It will change the contrast on the screen. So that the lines get darker. Now let's try this again. Look at that detail. You see that? Look at the detail. Yeah. It's almost too much detail. I'm going to hit the seconds over here and back out, make it 5 milliseconds per division. That's more like it right there. Let's slow it down a little bit more. Let's slow it down some more. It's a little bit too fast. And if it's jerky, that's not good. We won't have it if it's jerky, that's not good. Open it up a little bit. It's just jerking. It's going up nice. That's about as good as you're going to get right there. That's it. Is that okay? That's it. So does everybody see the pulses that are there?
Yeah.
You've actually got a spike on one of them. Little spike there. Now I'm going to position. I'm going to move that top. I'm going to move because they're too close together. So let's see. Move. If I move, hit move. And it let me move the top one. Okay. So let's try it again.
I'm trying to catch
Just move it back down. Okay. A move. And then B move. Now let's try it again. I've got the lines positioned on the screen, but we're hopefully we can see the wave better. Now that's better. You see that? You can see the two signals better.
You got to draw on the top.
Okay. So anyway, that's about as good as you need to ask for as far as the image of it. You're seeing two pulses and you're seeing one go one way and one go the other. This image doesn't look exactly like the book, but it does show up being opposite. It's not that had probe on there, so we'll let somebody else come over and do the probe.
His hands get tired after that.
Yeah, yeah, oh yeah, yeah. Mhm. As long as you got something that's approximately like that, it's fine. Yeah.
That's what I heard.
Okay, somebody else want to probe it, get another team. If you just wanted to look at where it's being probed at, you could sort of have it swap down and you do that, as long as you see where the connections are, you see that, that'll be fine. criticize his artwork.
That's the closest you gonna get, but you're drawing on the wrong one.
Yeah.
Don't you recognize fine art?
Oh, yeah, draw on file?
Yeah, you got drawing on file.
Yeah, it's gonna be up in here.
Hey, what would you use one of those basic?
Aren't you a connoisseur of art?
No.
Don't you don't recognize.
Cause his
You
part
don't
gonna look at.
recognize
Look
fine
here.
artistry.
Can I see that? They have to draw that.
I probably had to draw back here.
No, it's on
I
file.
figured I'd give you a space on that to draw.
Right, yeah.
Make it nice.
What they wanted you to do is they wanted you to put a meter on there and find out you can't read it. And then they will come up and tell you. And they're coming up and telling you.
Because it says, with what alternative instrument can
It
this be
says
solved?
what alternative instrument can be used. So if you want to go in there and say that you're using a scope meter,
It's got its line.
and then drop the pulse.
It's got its line. Right.
It's one of the few things that you have to use a scope. You have to use a scope for this.
Just to
There's
get the
nothing
wire
else.
hold it right. You got your live wire place to be
Look, so just drawing.
I got it.
It's only 110 or. I mean, sometimes.
Got the idea, man.
You need to get that electric bits that way.
It's not. We'll flip it around, you can see directly yourself. This is my common. It is common. I want to make sure that's what I'm talking. You can put, say, the red plug on line 22 and then the gray on line 23, common on 25. So you can go straight to the input module down there. Yeah. Slot 3.
I have a problem with two on the back.
I-22, I-23. Yep. Put, say, red on I-22, gray on I-23, and then put the black on common on wire 25. You got that black plug on 25? You do? Wire 25?
Yeah, that's what I said. And I looked at my wife, I said, sure is. Boy, I'm doing good.
Hmm.
Yeah. 20 years.
Very carefully.
Ah, yeah, you're making fun of me earlier.
Ain't that fun?
He was talking junk to me.
I wish you could see the thing in the hole.
All right, I think I got it. You think you got it? No, you still ain't got something right. You got it on 20.
Well, you got one of them's okay, and the other one is like,
Yeah, 23, 24, and then 25 is common. Common's all the way at the top.
look, I'm gonna flip this thing around and you look at the screen up there. You look at the screen up top.
I thought you said 22.
No, 23, 24.
That's easier then.
Wrong one.
Oh, they 24 and 23.
I-22, I-23, and then wire 25. Wire 25 with the black plug.
The one that's in your left hand.
Still, quit putting it in the wrong hole, come on now.
Is it?
Probably.
Okay, so now, this has to be in motion, doing
There you go. There you go.
I may not have been on that.
it. One of them was really
Still
not
ain't,
super
still
high,
ain't,
though.
still ain't hitting what it's supposed to be. You can touch it a little more.
Right now, I got a good mix on both of them now. You reading right now?
Yeah, but one of them was way too big. That black coach got me concerned. Is it on wire 25?
No, he's not. 25 all that top. All the way top.
25?
There's nothing in it.
No,
I mean, it don't look like it. Look at it. Yeah. Right now.
Something's still out of whack here. No, look, look.
223?
It's 22, I-22, I-23, and then wire 25 for common. But I thought wire 25 was at the bottom of the model.
No, it's
It's at the top, I-25 is, okay. As long as you see it up there. Wire 25.
Yeah, it's 45. I was right.
Now, so one of these posts that I've got to move, something got repositioned. So hold on, let me do a move here of one of the posts and see.
There you go.
Hey,
That makes it easier. Sir, would you break it? Is that the problem here?
no, I've got when we jog it, let me do it again. So the B posts I've got to move, the B posts I have to move it. Just keep watching here.
I can't see it. Oh, I can watch on screen.
That screen over there you want.
I can't see that one.
Open your eyes.
You move the A posts down. I got to get them repositioned. When the meter got moved, something went wrong there. Again. The A looks good, but that B is like way too big for some weird reason.
Definitely on.
Yeah, something, yeah, I'm not sure what's going on with that B. Let me move it down some.
This one,
And move the B wave, move it down some. And then move A. Again. You notice that the top one is like way bigger for some reason.
Well, I think they were reading something else. They were using different points. Because he was using 24 and 23, and then he wasn't even using the common.
Yeah, we wasn't even on the common. We thought the common was on the way up top.
The common's in the second.
Then said the second.
But something's wrong though. I mean, something's wrong because the signals are not the same size. I mean, they're not the same size. One of them.
Well, I can move the common. I'm gonna take up to the common. They did it right now.
What wire number is that though?
There is no wire. There's no.
I can tell you, you got a screwdriver. I can tell you which one that common is. It is cool.
Look on the door. Look on the door on the door. Where does it say common?
Common, is third one.
Third one.
But that's not.
Go by the door, but there's nothing there.
Well, there's something in the third one. I can't tell you.
try it, see what happens.
I'm gonna try the third one, I can't tell what it is because it's the wires.
That's what we were trying to figure out.
I just know a while ago, the pulses were more uniform than what they are now. Now let me move now. Just stay where you are.
Yeah.
Now it's starting to look more like.
Take your gray probe away. Let's just do one channel. Let's figure out one channel at a time. Go with the red, put the red on I-22 and put the black probe on 25. Let's look at one channel at a time and get the screen straightened out because there's something wrong.
All right, good.
Now, you're on the A channel. When you move the A channel up, so the A pulse is looking good. You see that?
Yeah, I saw it. I was looking at it. Yeah.
That's looking the way it needs to look right there.
All right, so it's like it's people.
Do the B only.
The only, right now.
So the B has the amplitude is way bigger for some reason on the B pulse.
All right.
And so there's something wrong with the B. Now listen, do this. Put the red probe where you have the gray one.
Red probe, right.
In other words, put.
All right, try it now. So I'm on the B now.
We're going to use the red probe to check the other input.
Okay.
And it looks the way it's supposed to. See?
Yeah.
It looks normal. That looks
All right.
normal.
Let's use the gray probe to check A now then. Did that.
Exactly. There's something wrong with the B channel. The B channel is not set up right with the stuff. That's what's wrong.
We're gonna go. Just put the on.
Oh, I'm in the wrong one. I was in the empty
So
one.
the B channel, there's something wrong with it. It doesn't have to look. Let me go to the B channel.
There's the B channel with it.
Ooh. Now what I'm saying is, I've got to do some adjustments here on the B channel. You got to leave the probes on there.
Oh, I thought you were done.
No, we're not done with that channel. Yeah.
I'll start. Go ahead. I'm on the A channel right now.
There's something funky going on with that gray probe. That gray probe is something going on.
What, ain't good?
It's showing overload. What it's showing. Well, it's showing overload.
So here's my question. The common, he said 25, right?
Yeah.
Well, wire 25 is not hooked up to the common according to this. Let me get in here. You got something, well, I can't get to what it is. The 25 is right there. Is that 25 is that wire right there? And it's going output 2. But I can't get back here to see what that is because everything's so tight. I'm gonna try to use this probe.
He says right now, the numbers you got now.
What wire number, let me kind of scoot back some, let me see what, let me get my eyeball in here.
Okay, so ELC common.
It's third terminal, and what wire number is it?
I can't get to, I gotta move stuff around to get to it.
Well, that's fine, go ahead and do something around there.
That's what I'm trying to do right here. Okay, there's 25 on there too, but you got 25 on the output too also.
Don't go to output 2.
Yeah, no. That's what I was on at first, you said wire 25. But then you said common, I switched to that. So you got 2 different wires 25 on there.
It's the second terminal on the left, at that 25.
That's 25, but this right here, this third one was also 25, which is your out, DC common. So, yeah,
That says 26.
oh, that's at 26. Okay.
That says 26.
No, that's 25, that's 25. Is that better to be on 25?
I see, that's 25, yeah. Go to that one.
Yeah, okay. Cool.
Now, you're on a dead terminal. You're on a dead terminal, the wires, there's nothing going there. You're on a dead terminal.
1, 2, 3. So we need to be on this.
Well, where that wire, the wire you're pointing at is going down here, ain't it?
I can't tell. Yeah, it is.
Huh? It's the fourth terminal, ain't it?
Yeah. All right. Think I'm on to it right now. I'm good. Your A or B? I'm on that.
It's reading OL. It's reading OL like there's too much voltage on it. It's just too much voltage on that line. That's something. I gotta get close. I gotta get close. It's not something close. Terminal 8, it's showing a terminal 8 and terminal 10 on the PLC. See if we go terminal 8, terminal 10
On the PLC itself.
on that module. It's not even reading his terminal numbers there. But bottom line, wire 25 is what we gotta be going to. Just go to that 25 right there.
Okay, that's what I was in. I started off.
Go back to there,
All right.
and then go to I-22, and just put the auger. It's saying OL. Now go back to that, remove the gray probe and just do the red probe on it. It's reading properly. The red probe is doing fine, the gray probe is not. So there's something going on with that probe. Let's switch these right here and see if the probe itself or if something in channel. So we'll put the gray probe in the real red channel.
All right, I'm
So use the gray, use the gray probe.
And the variable curve. In 8 channels,
And it's reading properly.
okay, I'm going to go to the red. Good.
It's reading OL. It's reading OL. So it's a range issue on the B channel. So let's go in the B channel. Now do it again. I bet you $5 I bumped that range on with and screwed it up. I bet you I did that. I bet you money I did that.
Go ahead.
Did you go ahead and see the ELC read to that?
10 volt per division, 20 volt per division. They're both on 10 volt per division right now. It's still saying OL.
So what's that mean? 10 volts per division.
What it means that it's saying OL. It's saying OL. With the red probe going into the A channel. Let me do this. Let's just cut it off and reboot it because there's something screwed up with it. Okay? We're going to reboot it. It's going to be happen, man. I'm serious. This can't be so darn hard, man. I'm serious. So now, we rebooted the thing. Now put that gray probe back on there. We're going to get it fixed here just a minute. Now it's fine. The gray probe will be fine.
Well, we have,
Yeah, if you switch them.
yeah,
We switch from now
The red
red
one.
one.
to that, okay? It's still seeing overload on the B channel. So that's the issue. The issue is the B channel is getting overload. It's seeing too much voltage there. Put your probe back on there again.
Put it on the road.
The red one. Just reading OL.
Reboot the thing. Maybe a hiccup in the ELC.
The best thing to do at this point, let's go auto. Now I hit auto and let it sort of do its own thing in auto. When you hit auto, the scope does its own measurements. It does its own ranging and everything. So now it's not saying, oh, well, it's another mistake.
Yeah.
And let me move and, now put the gray probe. Now you want to be able to read both channels at the same time.
Both of them?
Yeah, on both of them.
Okay, so,
There's one of them on 22, I-22, one of them
got it
on
with
21.
one.
Right, we're going square. Well, let's just hold on. I put scope in automatic. And we're gonna see when it does its own, settings, is it gonna quit reading the OL? And it did. Now look. Now you're getting, so listen, all I did, listen, I hit the automatic button here, there's an auto button here, watch. There's a green button, let me just same position right here. Let's get it up. I want everybody to see this real good here. This is stuff that's it's hard. Now, I could not adjust it so that it would quit saying OL on that channel. So I hit all of it. When you hit all of it, what it does is it lets the oscilloscope decide all of the settings and all the resolution adjustments itself. It puts it on autopilot. And it tries to optimize all the settings itself by itself.
It's kind of like when you're multimeter,
Right. It basically it puts it in a completely automatic mode to where it does its own thing, and that's where it straightens itself out. Okay. So let's go look again. Now that's actually showing you the 90-degree lag that I couldn't see a while ago. You see that? You see the 90-degree where it's splitting? Look at that. Listen, man, that's as pretty as you can ask for right there. You see the 90-degree split? Listen, that right there, you see that? You see the 90-degree lag on one of them? I couldn't even get that a while ago when I was, basically, I shouldn't have touched it. Now, every other time I've messed with it, I've been able to get it like I wanted it. But this time, something went wrong with what I did. And so, if all else fails, you get automatic. Let the darn thing do it itself. This is the best reading. I mean, this is really, a really great reading right here. I'm you see that? And it's showing that 90-degree lag. It's showing it dead on. How many it's dead on? Let's do it again. Whoa, look at that. Look at that. Man, it's got that 90-degree lag in there. Google Mooga. Well, that Grady on San Francisco said, good Google Mooga. Good Google Mooga. Huh? I'm gonna let go of it. Good Google Mooga, man. Look at that. That's it. That's it. Let me get closer. Let's get down in there real close here. Real close. Now, one more shot here. One more shot up close. If somebody else wants to come around and close it. But hey, that green hollow button, that's the best thing. Sometimes I want to stretch something out and be able to see more detail, and this time it didn't. Well out of there, you know. Honestly, I've never had that much trouble with it. I've always been able to get in there and fine tune and change the time resolution to see more detail. But this time it screwed up the amplitude part where it said, oh well, it messed me up there, you know. But hey, these scopes right here, they got the auto button, the older style CRT with the picture tubes, the old big ones. They didn't have no auto button on them. They didn't have it.
You screwed that one up, you're in trouble.
You
screwed that one up, you're in trouble.
Yeah, but the older style, you had everything was completely manual, and it took you forever sometimes to do it. Yeah, you go I-22 with red, I-23 with gray, and then wire 25 is black. It's a black probe. Beautiful, absolutely beautiful. We're gonna come back on the upstroke. Absolutely beautiful, man. Hey, you can't beat that picture. You cannot beat that. That picture is it. That's on point, man. You see it? It agrees with the data sheet that it shows that 90-degree lag of that signal. See it? Huh? Now, this is where tomorrow with Butterball, when they come back in, I'm going to have them doing this because one of the guys told me they change out encoders at times and they don't even know for sure if that's what's wrong, and part of the time it ain't, you know. So, and they got those high-speed input cards like that that can count the impulses. They have those. I think they'll be just swapping stuff out till they figure out what it is. Now we can get into another night. We'll get into the PLC program and let you see how the logic is actually counting the pulses in the program, and you can see where it does count. And it compares the count to some reference values that are in there, stored in there to know what kind of what does it have. You know, okay. Anyway, I'm sorry it took so long, but hey, let me tell you, there's not a lot of people that knows. I mean, that can take one of these and set it up and do it. Again, you're just in a nutshell. You hit that auto button now. You hit that green auto button. Is the best way to do it is if when you try to fine tune, and normally I can fine tune. Normally I can get out of all those and I can do more detail. I like to see the waves a little bigger, you know. But it just didn't want to agree with me, so I hit all those. And this got the
You ain't got 90 degrees. I think, right?
well, you could be missing one of the signals, or one of them could look totally unrecognizable. They both got to look like square waves, and one of them's going to be 90 degrees behind the other. You know, when you go back to the data sheet, where I showed you, where's the if you go back, where's the let me pull the data sheet back up. Is it a PDF? Right there. So you okay now, so what you're seeing, you saw those superimposed on each other like that. You saw them superimposed on each other. That's what you saw. If let's say if one of these is missing, or if they don't have that square pulse appearance to them, if they don't look like sharp square waves, there's something wrong. You know what I mean? That's basically it. But what you saw those two waves move superimposed on each other, which is really great because you could actually see that 90-degree lag. I couldn't see it when I had them separated. When I had the waves separated, you couldn't see the difference. You couldn't see the timing. So actually, I'm kind of glad it happened, because it looks way better when you see them superimposed that way. It looks better. You can really diagnose it much better like that. I've never even hit the auto and seen it go that good in auto, never. That's why I've always kind of fiddled with it to get it a little easier to see. It did really good. The best I've ever seen it right there in auto, honestly. But to see these encoders, again, not many of them are linear. Most of them are rotary, and they'll be on the back of the motor, and they're going to be picking up rotary information about where something is, like on servos. Servos at your plant, or servos on the robots or on mill machines that are automatic CNC mills. So it's a big thing. I've requested, I have put in an order to get some servos. Alan Bradley, Kinetics 5500, the new, just the what's popular now. If we would set them up on the board and then learn how to wire the program.
If you didn't have it, how would you check that?
You couldn't. You just swap it out and put another one on there. I like what Butterball's been doing. But what's puzzling me is that they sent this over here from Swain. They done that in school. And yet the guys going to this particular class they don't know that there's where they can get one. But they're going to go back and ask, I see, especially after tomorrow.
I guarantee
that, we only had one scope, but it was a big, with a big picture put on it. It was old time.
Ours was similar to that. I've only seen it one time. And I don't know what the model is, but it's similar to that. Engineers have. They take it to the test tower.
Right.
That's the only line they're seeing.
Well, see, if you put that on a regular AC coming in, put that on, go to one of them and go from your power line, go from it's LO1 and NO1. You can see the regular sound wave coming, the regular power coming in.
She said LO1
And NO1. Or either LO3, NO3, and NO3. Mm-hmm. Now, see, you're looking at the, hold on, you need to go, not with the gray plug, but just use red plug and the common.
Oh, I think you think of that.
You won't use the one channel.
I kind of have that. Before you come.
The NO3. Now it's saying, oh, well, hold on, we can get all of it. What it's showing static here because this is floating. Let's get this here out of the picture, or you can. A channel, let me go to A channel and put it on. You can cut the B channel off and not the A channel. B channel off, so go see it here, and just go to the A channel. I've never noticed that. You can't cut the A off. Yeah, it's picking up static out there. It is in millivolts. It all the ranges in millivolts. So this is the AC coming in right there. See how it automatically adjusted if you get it nice and still. Now, you see how tight that is? I can go in there and stretch that out. Let's go back on it again. I can go in manual and stretch it out and change the time on it. So it's something land. Okay. Yeah, appreciate you coming. Thank you. Hey, ask your electrical guy over there if he's got a scope meter in there anywhere. Ask your electrical guy. Now, you don't have an engineer. Okay. Okay. Do y'all have, you got any coders on some of your machines?
We do. Matter of fact, I told you, a couple of weeks ago, they thought there was a motor that was bad. And they ordered another, but it wasn't.
Right.
So we need to tell them to take to the machine out here. I forgot when they found they ordered it, they're going to.
Now here's what you need to find out. You need to find out if the encoder, if you got terminals you can get to measure, if you can measure. Some of them encoders got a jack that goes back to drive and you can't even get to the line. Then you can put it in software. You'd have to have software for that drive and go in there and you would see this in the software. It would have a scope view in the software. So it's one or the other. But your more advanced stuff, where if it's just jack plugged in and you can't even get to the terminal, it'll be a software visible. You get in there somewhere and it's going to show you this picture. Yeah.
That is crazy.
All right, yeah.
Have a good one. Well, see, but you look at it, it's down in millivolts. So you see the millivolts. A millivolt is 1,000th of a volt. It's 1,000th of a volt.
That would be your coils.
It's magnetic radiation in the air near that near the strip. I took it out of all of them, went back to manual, and that's just as pretty as you can ask for. That's a true sound wave right there coming in from both ends. Get 116.4 Pulse RMS. But I had to toggle out all the manual and all of it, and then it readjusted, and then it got it right. So the best thing if you get around one of these things, this is your go-to button. I'll get that all of it. Yep, and just you may have to toggle out all of them back in.
Right now, they're running, it's just like this, it's just
1600, so they come down.
we had the kids. It's like that. It's a bunch of stuff. Which is that one.
They come down then. They come down. That's actually a good price. It's for what it is. It's a good price. Yeah. Because nothing else, there's nothing else that's going to tell you if that encoder's in the good or not. There's no way to know it without a scope.
Are encoders used on all those machines?
They are a lot.
So
A lot.
what exactly is it used? Because we can't even use that as a market or certain stuff.
What it does is it measures the height of that. You've got higher and lower pass, they're shorter than each other. If you look here, now that's the thing you can do it, it'll line up there.
So what would be the difference between something like this versus what you use for the?
Now, the only reason they use different stuff, that's digital work, that's analog.
Okay, I got it.
That's analog, 0 to 10 volt.
That's only the.
It's analog, and that's digital.
I got it.
They just got it different, so you can find out you can measure with analog devices, you can measure with digital devices.
That's the only thing.
So that model, get those two inputs off the A and the B. It's a high-speed channel input module, and it can channel super high changing, fast changing speed or signal. But you can have a motor. You can have a motor encode back of it, and as that thing turns, it's sending them pulses back to your drive, and it knows where the motor is. It knows position. Like where I worked at, we had automated welding equipment. So we had welding fixtures that ladies with little wires in the panel, and they hit a button, and the welding table would go under some guns. And there was a chain drive that pulled it under a weld bridge with a bunch of automatic guns. So it would go under there and stop at a particular position in millimeters from home. And it would, all the guns come down, they would weld, da 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 da, and then the guns would come up, and then the servo would pull the chain to the next spot. And the servo had an encoder. It went back to the PLC, to the control, and it knew how far to go, and it knew where to stop based on the encoder pulse coming back from the servo. It pulled that chain in. So it knew where to stop to do the welding in. Yeah. Mm-hmm. Yeah. Let's say on more easier terms to look at, if you've ever seen a lathe or a mill machine run a CNC mill machine. You ever seen an automatic mill machine running doing cutting metal now? Same thing. All of those cutters, the motors that move the cutters around and all, they've all got encoders on, and they're all being told where to go, and the pulses are letting them know how much further to go and cut to do automatic cutting. It's all about position. It's all about position. Mm-hmm. Yeah. There's a blue million things you can use it for. Kind of in a more basic sense, on your vehicle, there's a wheel speed sensor on your wheels, and it sends pulses back to your PLC in your vehicle, what they call computer's PLC. But there's a wheel speed sensor on all your wheels, and it sends pulses back to know. It uses it in for non-skid, to where if you have anti-lock brakes, if it knows that it can tell if you're in icy conditions by wheel speed and the way your brakes are going all the way. But anyway, you got the pulses coming off of your wheel speed sensor, and it's not exactly an encoder, but it actually kind of is an encoder. It's sending pulses back. It is a type of an encoder on your wheels. And so if they can go bad, but when it goes bad, you'll be at shot. Yeah. So, yeah. But So you can read regular AC signals, you can read decoder signals, you can read flat out plain old DC. And notice DC plain is a flat line. If you put that on the 24-volt DC line, it's just going to be a flat line straight. And so, you know, the sign. And if you read the VFD, we can do that another night. The variable frequency drive, if you read it, it's going to give you square waves coming out of it at some frequency, whatever you set the motor for. And that's a funky looking wave too. It's weird looking, but it's square, but it's funky looking. But this will read the VFD output. So all of your drives out there that you're using for variable speed, you know, you can put that on the output going to the motor. It'll read high volt. It'll read like 480 volt VFD on the waves. Mm-hmm. Well, coming out of the drive going to the motor, you can read it directly on the motor lead going to the motor. It'll show you the VFD signal going out there to it. We'll do it another night. You know, we could do it say Thursday night if you want to do it. I haven't been told I don't know when it's going to be offered. I know what the new class I got for summertime is electrical estimating. It's a new one. I just got the book in today. I don't even know. The last I looked on Web Advisor, they don't even have the classes in. I don't even know what I'm not sure what it'll be. I don't know for sure. But I hope they don't wait too late to decide. I gotta have time to get ready for whatever it is. You know what I mean? Hey, nobody even told me. No, I got on Web Advisor just started looking. That's how I know. And you can't be told. Yeah.